Rajat Gupta is a co-founder and director of Sensonics Devices Private Limited, where he is researching solutions in medical electronics and personal health monitoring devices, embedded processors, and power-efficient circuits in scientific computing. And Yogesh Tripathi is RTL design engineer with 5 years plus experience. He holds a BTech degree in electronics and communications. So with this, I will hand over to Rajat Gupta.
Welcome, ladies and gentlemen, to my tutorial on the logic design of a RISC-V microprocessor. Some of you may have wandered in out of curiosity, wondering what role does a logic design tutorial have in a VLSI conference in its 35th year of existence. Hopefully over the period of the next 90 minutes or so, I will be able to answer that question as well as the logic design methodology that I'm going to be talking about in this tutorial. A custom microprocessor can bring about a paradigm shift in logic design. It can bring about orders of magnitude improvement in designer productivity. How does that happen? It happens because you're designing a piece of hardware once with all its timing closure and design for test and so on, all those overheads. And then you can write code in its assembly and design different and obtain different pieces of logic, completely different pieces of logic over a period of time. And in each piece of logic that you design, you don't have to go about designing the microprocessor from first principles. Obviously, this is not applicable to all kinds of applications. So for each application, you would need to be able to design a different microprocessor, probably. Maybe a small change to instruction set, maybe a few additional instructions and so on. You can imagine that a custom microprocessor like this in your repertoire of logic as a logic designer is like having a Swiss knife while you're in the forest. And key, of course, here is that you should be able to design a microprocessor from first principles. That is key. And understand that while you know design of state machines, you've learned that, you've used that. The problem with the microprocessor design is that here is a book-length document, which is an English document, which somehow has to be translated into the corresponding state machines. Once it reaches the state machine, you can use the skills that you've learned in college and you have used over the years to convert that into the microprocessor that you set out to design. That is the discussion of subject of today's talk. How to translate that booklet document systematically into a set of numbers that will be your state machine specifications. Okay, and also understand that the RISC-V ISA and its corresponding IP collateral assets such as compiler and the toolchain and so on, available freely in the public domain, makes it a very attractive starting candidate for a class of designs based around the RISC-V. So you can have more instructions, you can have less instructions and so on. I'll discuss why the RISC-V is particularly attractive from this perspective, and you could use that for all of your designs. The problem here is that, or the question that you might have is that, okay, so there are so many RISC-V codes available both in the academic as well as in the commercial domains, which is available for free download. Why another one? Why do I need to build another one? I can take that code and use it. Not true. There are exceptional reasons why you would need to be able to download your own, build your own code so that you don't need to download something that's available from the off the shelf. If you had your own microprocessor, one of the things you wouldn't have to worry about is Trojans that you might have to worry about if you had downloaded a piece of code from somewhere. But more importantly, or equally importantly, you can design any piece of logic. For example, an FFT engine. You could simply by writing code into your targeting your engine. So writing code in the assembly or whatever, you could write it at a high level and then assemble it and produce object and so on. But what would happen is that while you're writing that code, as I described, maybe an FFT engine, you might want to do a little bit of additional code to improve its efficiency. Maybe the reverse binary addressing would be a little piece of logic you would put into the addressing logic, and you would enable that by some mechanism, which you will implement into your microprocessor, and the rest of it stays as before. Okay, so this is something that you could do. And then once you've implemented it, you could take a look at all the instructions that you have not used from that engine, from the RISC-V, and delete those instructions, the corresponding data path elements, the corresponding control elements. And now, and you have already added, if necessary, some additional logic. And then this piece becomes a customized piece, very efficient, and based out of logic that you have designed, the completion of which you have done through your RISC-V design, and therefore the amount of effort that it takes you to build this is orders of magnitude less than if you had to build an FFT engine from start. You could do a completely different piece of logic where maybe you have to add substantial pieces of hardware, for example, a math engine. Oh, similarly, if you were to download a piece of code, and let's say you thought that here is a RISC-V that I want to use, but it has a floating point engine which you're not interested in. How do you remove that floating point engine from the hardware? Until you get inside the mind of the original designer, it may not be easy to get rid of both the data path as well as the control elements associated with the floating point engine. You know, how it handles the exceptions, how it handles. So it's not very easy. If you have built it, you would be able to do that. And if you have built it in a manner that allows you to make such changes, or is designed to allow you to make such changes, it is that much easier for you. So this is what the subject of our tutorial today will be. And this you'll be able to do, apply these design approaches and build a microprocessor, the logic design of the microprocessor. You should be able to do that whether you have access to only a laptop and Excel, or you're a professional working in the industry and access to millions of dollars of high-end EDA. You can apply it in both cases, with the difference that if you have got high-quality tools, you would adapt the techniques that I'm talking about to slightly different approaches that will give you even higher productivity enhancement. If on the other hand you have only a laptop and an Excel, you still can do it, but it might take a little bit more time. Okay, so perhaps you agree that it may be a good idea to have your own microprocessor. But why RISC-V? It could be any other microprocessor. Well, as you know, Intel or ARM, the microprocessors, ISAs are not freely available. Even to get started, there'll be a huge cost. On the other hand, RISC-V has a freely available ISA, well documented and so on. And that becomes a tremendous incentive to invest in R&D and build around this background. The other thing is that, remember that if more people start adopting RISC-V, then you have, because of its freely available ISA, you have a very interesting mechanism by which interoperability, second sourcing, is available from your competitors. So your customer can rely on your competitors to provide second source for your design. Well, there is a little bit of catch here. First problem is that let's imagine that the piece of hardware you built had IP that you built had some extra instructions, custom instructions, or you deleted some instructions. In the latter case, there's no problem. In the former case, yes, there could be a problem. But while you're developing the IP, you could actually spec it in such a way that should there be a piece of hardware that was not aware of the custom hardware that you built in, it could be a requirement for the IP that you make available to your customer. If it didn't have if there is another RISC-V which didn't have this piece of hardware, it should be able to emulate that in software. And how would it know whether it has or doesn't have that piece of hardware? There is a mechanism. RISC-V supports that mechanism. So with this, what happens is that you could potentially have a common toolchain with incompatible software variants. So I could have, for example, this would apply beautifully for a very large organization where different departments are using different variants of RISC-V, and those variants could be incompatible with variants used in another department. Or it could be in the academics, where you have one department producing a RISC-V in the same institute, producing a RISC-V piece of based hardware, and another department in that same institute producing another RISC-V, and these two have incompatible code. They could both coexist on a common tool chain. Why and how? By a mechanism which is described very well, but that document is still a work in progress. This is described very well in the privileged document of RISC-V. I will not talk too much, except in passing. I will not refer to the privilege instruction. There are not too many, and I won't be referring too many to the privilege instructions or the privilege documentation. But suffice it to know that RISC-V has a mechanism which they call the control and status register, CSRs, and there's a bunch of well-defined CSRs. Those CSRs, the specific ones that you might want to look at, are the ones called the machine ISA MISA, and the machine vendor ID called M vendor ID, and the machine architecture ID called the M arc ID, and the machine implementation ID called the MIMPID. These four CSRs can be set up suitably so that at the time of at the time of code generation, the compiler could actually produce code, given the appropriate definitions for MISA, M vendor ID, and so on, could actually create branches in the main code. So incompatible pieces of code can be integrated on a common compiler framework. You have to put that in place, but it exists. And with that, you could actually additionally also put in a mechanism by which if you have a code which is meant for a certain way, intended for a certain vendor ID implementation, and you know that the vendor ID from the architecture ID, you know which pieces of hardware doesn't exist in the current target, you can always fall back and replace the hardware that one version produces with software which is meant for the other version. This is very easily and eminently doable. So you can have a mechanism where different people can work on the same architecture and provide solutions to a common good, which means that in India, we could have all the institutes, academic institutes, producing code, different applications. Somebody produces a matrix engine, somebody produces a math engine, FFT engine, whatever, and image processing, so on, different areas. And these could be available on a common tool chain. And this IP base begins to expand now, which means that we have also a mechanism to expand on our IP base, which currently has not happened. In lots of places it hasn't happened, not just in India, but in India we've been seeing that very intensely. And this provides such a mechanism. While and you understand that when you come up with the next version, RISC Foundation comes up with the next version of the RISC-V, adds more to it, the software automatically your IPs automatically scale with the software upgrades. Okay, so now we are sure that it's RISC-V that we want to focus on. And a quick recap before we actually get started with the design methodology discussion. Quick recap between CISC and RISC. Both terms were coined in 1981 in the first paper on RISC that Professor David Patterson of Berkeley wrote, where I think the paper was titled, I vaguely remember, a VLSI RISC. I couldn't find that paper though. Some other versions are there, but that original paper, I don't know where it is now. But anyway, the idea is that the design approaches that were being used until that point, the basic paradigm was that a microprocessor, a more advanced microprocessor, should bridge the semantic gap to a high-level language more closely than the previous generation microprocessor. And therefore, programs which are written in high-level language will compile to very compact code in the target complex instruction set. The RISC-V, not the RISC-V, the RISC-1 actually that time, the RISC came up with a different paradigm. It said that the first thing that it would operate only on instructions. The entire idea was that instead of using complex addressing modes, it will have a very simple addressing mode. There's only a load and a store to reach memory, no other. There's an implicit addressing, which is instruction fetch, but we don't talk about that. And it will operate, all instructions will operate register to register. So there'll be a register file, and source and destination data will be stored in these registers on chip. And every instruction will execute in one cycle. It will have a very limited instruction repertoire. That's how the reduced term came in. This will allow the control to be very simplified, and hopefully will allow the clock to be very fast. Much faster than the clock you would be able to achieve in a CISC. The other thing was, again, to simplify control, the idea was that the instruction opcode fields would be orthogonal, meaning that you don't need one field to be decoded before you can decode the other field. You can decode each field independently. And this has challenges up to 16-bit processors, 16-bit instructions. You will have challenges. There have been challenges, and we will maybe see some of those as we walk through. And but in 32-bit, the problem reduces significantly, and beyond that, obviously, it can become a non-issue. Implementing instructions such that you have orthogonal fields. This is what a RISC is. We will not discuss CISCs further in this talk, but again, suffice it to know that the method we will use today works as well for CISC. In fact, it works better for CISCs, and was in fact invented by Nick Tredennick, who developed this technique, which I am going to be talking about, developed this technique in the 1970s to design the 68,000 microprocessor. And the superiority of this technique over any other technique you use to design microprocessors will become very evident when you attempt to design CISCs. All that I did was adapted it over the period of years, adapted Nick Tredennick's technique, which is meant for CISCs, to RISC, which has a much simpler instruction repertoire, so the flowcharts can be much simpler, but which, in order to function at function superior, better than the CISC, it has to be pipelined, and that pipelining had to be built into the scheme into the flowchart scheme. These are the only two adaptations I did, and which is what I'm going to be talking about. And it is also another thing that, although I don't know for sure, but I suspect that CISCs today, the Intel processors are all Intel architecture. The x86 architecture is a CISC. I suspect that it is basically, don't know for sure, direct info, but I suspect that it probably is a RISC engine of some sort at the base, and the entire CISC ISA is the RISC engine underneath emulates the CISC ISA that they adapt on. So even if you want to build a CISC engine, you probably would be better off building a RISC at the base and then adapting it to a CISC in terms of an emulation of the RISC host targeting the CISC guessed. Excuse me. The bottom line is that whether CISC is better or RISC is better, we don't enter that argument. But the bottom line is that in the case of a RISC, what you have is you have a little more opportunity to innovate, in the sense that, so you reduce the control. You reduced, you simplified logic so that you have a faster clock. So your silicon real estate usage is significantly less than a corresponding CISC under a minimal configuration. Now, you have to compare the two at equal silicon real estate. So that now that you've got all these extra silicon real estate available when you attempted a RISC ISA, what are you going to do with the extra real estate to compare with the minimal configuration of a CISC in order to be able to compare whether you are better or the CISC is better? And the standard practice is that the total time to execute something, an instruction or a program, should be, in one case, the number of cycles. In the case of RISC, the number of instructions will be more, but the time per instruction is less, average time per instruction is less. In the case of CISC, the number of instructions is less, but the average time per instruction is more. At equal silicon real estate, if you have architected your RISC properly, then you should be able to outperform the CISC. That's the basic idea here. And as you know, that memory accesses are expensive, and therefore both approaches will attempt to put as much memory on chip as possible. And in the case of RISC, you will put that via a register file, but you can additionally also put cache inside, both for instruction as well as for data. In the case of CISC, the mechanism of that register file doesn't exist, and therefore you might be a little you might give up a little bit of a handicap here. But regardless, the RISC-V is available for us to use, and that's the approach that we will show, and I'll try to describe how you could design a RISC-V. And when I'm saying a RISC-V, what I mean is RISC-V allows you to have custom instructions. As we discussed, these could be incompatible. So you could have many sets using the same opcode fields, free opcode fields. You could have many different pieces of RISC-Vs. And all of those pieces could coexist. You could instantiate a dozen RISC-Vs into your chip, each one doing a custom piece of work. And you could also have a single RISC-V operating as a full-fledged microprocessor for general purpose compute environments. You could even put an array of RISC-Vs and use that for a supercomputer type application. All those things are possible, but the basic building block is a single RISC-V, and that is what we are going to talk about next. How do you go about designing that? Before proceeding any further, let's scope out the areas we will not cover in today's talk. So for that, I thought I'd share with you my perception of a high-level microprocessor model. A microprocessor comprises four essential elements. The first piece is the instruction execute engine that executes all the instructions. The memory is the second piece, which comprises two parts, the program and the data memory. You could have both these memories integrated into a Princeton architecture, or they could remain separate on a Harvard architecture. But that's the memory piece. How you address it is part of the hardware that addresses the memory is part of the microprocessor design. When you're executing instructions, for some reason, sometimes the instruction cannot execute normally. There's a divide by zero or some other type of exception. At that point, the control of the instruction execution is transferred to a piece of hardware, another state machine, that handles those exceptions. We call that the exception handler. Now, the exception handler handles the instruction whenever there is any instruction that cannot proceed because of whatever reason, that is transferred to the exception handler. However, whenever there is an external hardware signal, a trigger signal that is intended to suspend the flow of instructions, that is called the interrupt service engine. So these are two pieces, two complementary pieces. One handles the when the instructions cannot flow properly for reasons of the instruction flow itself. We call that the exception handler. When the instructions are not allowed to flow for handling some other program or another set of instructions, that is the interrupt service engine. So these are the four pieces of the microprocessor that comprise the whole microprocessor from a hardware perspective. Of course, there's the tool chain and software and all that. I'm talking about the hardware. So today's talk, we will talk specifically about the instruction execute engine. As you would know, that's the design of this piece is the mysterious piece. This is the piece that people don't usually design. This is what when you license a microprocessor, this is what you're using it primarily for. You will probably modify the memory mechanism. You will probably add to the, you probably won't add to the exception handler, but you will definitely add to the interrupt service engine. So the other pieces are pieces where you have interacted with other architectures, and you have mostly will have familiarity. Some of you may have familiarity with the instruction execute engine. For you, this talk might be a waste. But for the others who don't have exposure to designing the instruction execute engine, this is what the rest of the talk is going to focus on for a RISC-V ISA. The first thing that you do trying to design a microprocessor is to read the instruction set manual. In the case of RISC-V, that is the volume 1, which is called the user mode instructions or something like that. And that's the document you would read. And the way one would go about is to figure out first what the instruction classes are. And for those of you who have not read the RISC-V user mode document, I'll give a quick summary here. The instructions belong to 5 categories, and these are the integer instructions, which comprise the logic, shift, arithmetic, and so on. It comprises the load store instructions, the jump and branch instructions, and it has a few instructions for environmental control, break, and so on, how you allow the software to exit to a privilege mode, which, by the way, as I mentioned earlier, is covered under the volume 2, which is the privilege modes. And then there are the CSR instructions. How the CSR instructions are mostly going to be used in the privilege modes, but you have access in the user mode. Many of these instructions under CSR are going to be used in the privilege modes, and there are other constraints with reference to how the register set is defined in terms of its readability, writability, and so on for protection, which has a very well defined in the privilege document. Then it has the multiply and the divide instructions. It has atomic instructions meant for situations where you have your processor accessing shared memory, or where you have multiple processors accessing shared memory. And it has compressed instructions, which is a subset of the basic instructions which can be implemented as 16-bit, so that the compiler can reduce the code footprint by using compressed instructions to the extent possible when generating code for object code for programs that you might have written. And it has floating point instructions. These are the categories of instructions available on RISC-V. So you would, while trying to do the design, first thing that you would do is organize and figure out how what these instructions are, what these categories are. The exact binary opcodes and all that are not critical at this point. They are necessary, but they're not critical at this point. What I would do next is make a summary kind of a table. I'll show that next. So you can see here, this is a RISC-V instruction word. I've tried to organize that using different colors to show the fields. And as you can see, here, this is a 32 byte instruction. And these the first row, which is in gray, describes the bits. So 0, 1, 6, 2 to 6, 7 to 11, and so on, up to 31. And these are the first 2 bits. I'll talk about that. Very interesting how RISC-V has set this up. Very, very elegant. And the 2 to 6 is the opcode. So you can see that the opcode is completely orthogonal. Excepting that, there are some more fields. For example, if you see the function 3, which I've called the function 3, this is a 3-bit field that defines some sets of functions which go along with the opcode. For that opcode, there may be multiple functions which are defined by the function. This is largely orthogonal. There's one category of instruction, which is the jump and the some miscellaneous jump, which does not use this particular 3 bits for opcode decode. But otherwise, that's also orthogonal. Same thing true with something which we call the function 7, which is a 7-bit field. That is a little more scattered. As you can see here, source 1 and source 2 are the two sources for register to register operand, and the destination is another. For 2 sources with 1 destination, you have these 3 fields. As you can see, these are also mostly orthogonal, which means that you can decode these in parallel. So you don't have to wait to decode one to get to the next one. And that's what orthogonal opcodes meant for. And as you can see here, once you've structured it like this, this looks very, very elegant. We are not talking, by the way, about the actual bit patterns, but you need to. Whenever I start a design, I actually make an Excel and create all these bits and put those actual bit patterns there. We will use that. For actual design, we will need the bit patterns when you're decoding or whatever. So the first thing to do is to put that in. But another useful thing to do is to summarize it in this form, because this will let us create a first draft of our data path. See, from here, we can figure out how to build a data path. We know that we will need to have based on this function 3, and as you can see in the previous slide, we saw that we've got logic, arithmetic, and other functions. So those functions will need pieces of hardware. So there's a piece of hardware which will need 2 sources, will need a destination. All 3 come from the register file. Okay, so what do we do? Should we have a register file with only one address mechanism, that is a single port register file? We can do that. That will be a compliant RISC-V. It'll work slow. It'll need 3 cycles to, it'll need 2 cycles to fetch the 2 sources, then it'll need 1 cycle to write the destination. And even if you're able to do the computation in 1 cycle, you'll need 4 cycles to do this, and you can't pipeline. But you can do it. You can make a very, very small processor using that. I believe somebody has also done that. I vaguely remember seeing something on the web. Somebody has done that, I think. You can make a very small processor, maybe under 8,000 gates. And assuming you don't put a multiplier, you emulate the multiplier function. You can put that in a very small footprint. On the other hand, you might want to customize it to some other level. These are decisions that you can make. You can make it 1 port, 2 port, 3 port. You might even be able to, if you're doing a very deep pipeline, you might be, you might want to put even more ports than that, depending on how deep a pipeline you want to do. These are decisions at a high level that you would make. And as you go along the design process, you can actually change those decisions. If you don't want to change those decisions and you made one to start with, you go along the process, and then as you move along and start writing flowcharts, you will realize that there is a piece of hardware that you need to put. You stop the work there, build that piece of hardware, push it into your data path in a drawing, and then look at that to write your register transfers. There's another interesting thing that RISC-V has, is that the register file is 32 deep. So there are 32 registers, each of 32 bits. Now these 32 registers that are there, register 0 is actually a virtual register. It contains 0, and it cannot be written, obviously. And but it can be read, and whenever you read it, you get 0. So whenever you need 0 for something, you can read the register R0. But more interestingly, when you don't want to write anything, you can actually write to register 0, and the instruction would go through without the actual write, which means that many instructions can actually be pseudo instructions based on specific values assigned to source and destination registers. For example, as you can see here in this list, we don't have a no-op, but there are almost any instruction can be made into a no-op. You put, for example, you could put source 1 as, you could make a single instruction register with a source 1 as 0, as R0, destination as R0, and some operation, which operation doesn't matter what you're doing, because it will take 0 from something. You could have a second operand could be a immediate operand. In fact, they recommend you use the add immediate as the opcode, configured with R0 as one of the sources, immediate will be another 0, and destination is also R0. So there are many such things. In addition to that, RISC-V also has, interestingly, a mechanism by which you can add the instructions that are not defined, the pseudo instructions that are not defined. These are all there in the volume 1 of the document. So the pseudo instructions that you're not using can be used, the no-ops that can be used for hints to the to the hardware. There's a whole class of hints, which means that you have a no-op. For all practical purposes, it's a no-op. If the hardware didn't implement it, it would walk through the execution as a no-op. If the hardware knew what you were trying to talk about, that hint would let the hardware trigger into some other areas, and some dedicated hardware will work on that. So here is a similar summary for the compressed instruction word. The compressed instruction is a subset of the 32-bit instruction, excepting that this is 16 wide. And as you can see here, even here, the opcodes have been maintained orthogonal. The peach color, as before, is the opcode color. So those bits in the various instructions are meant for opcode. And as you can see here, the opcodes are also largely orthogonal. But there are many more instruction types called up uniquely here. The 32-bit instructions has many more instructions, 48 or something like that, which define all the instructions that RISC-V supports. But here, this is a subset of those 48 instructions, but you can see there are many more rows here. How this works, maybe I'll take a few minutes to explain. See, the way the compressed instruction works is that you would get this compressed instruction, and there would be a piece of logic inside your hardware, which is basically a piece of combinational logic that will expand the 16 bits into the 32-bit word, because there are some things are presumed here, like you have these accumulator-based instructions in 8085. This is similar to that. There are some instructions are R2-based, some instructions are R5 or R1 based, and so on. Those are implicit source or implicit destinations. And there's a well-defined way, and it's completely combinatorial. There's no state machine to translate from one to the other. So you would translate this into a 32-bit instruction, shove it into the pipe, and it would execute as a 32-bit instruction. That's how it's intended to work. How the thing is set up, as you can see here, that the LSB, the two LSBs are allowed to be for the 16-bit instruction 00, 01, or 10. 11 is not allowed. Whenever you have 11 for the two LSBs, it implies that this is a 32-bit instruction word and not a 16-bit instruction word. In fact, you could make, and that's how the RISC-V has been set up, that you could make even larger. For example, let me go back to the previous slide for a bit. Let me see how to get there. Oh no. So what happens here is that if you look at the previous slide, you would see that the LSBs, the two LSBs are 1, 1. When it is 1, 1, it's a 32-bit instruction. The next three slides, next three bits are, that's 2 to 6, which is next 5 bits. Those 5 bits, when they are all ones, they will be it will be a 64-bit instruction word. And when there are two options provided, when they are 0, 1, 1, 1, then that will be a 48-bit instruction. So what happens now is that excluding those 2 bits of code, those 2 codes for those 3 bits, those 5 bits, the rest are available for 32-bit instructions. So you can keep expanding on the instruction word simply by looking at the LSBs, and you can decode what they are from the LSBs, and the decode depth is only a 5-bit or a 7-bit single gate. This is how the thing has been set up. And the compressed instruction, why is it useful? It's very useful because you could be fetching a lot more instructions per memory fetch if you were looking at the compressed instruction word. Which means that, let's say you set your memory instruction fetch, the implicit load on the through the instruction fetch, maybe you make that 32 wide. Then with every instruction fetch, you get 1 instruction. So if there is any stall for any reason, the processor halts. But if you're able to compress and put a large number of instructions as 16-bit, with each fetch, you can get 2 instructions. Which means that for every instruction fetch, you have 2 instructions into the pipe. So if you have a halt for any reason, if you have a requirement to access the memory for any reason, the processor doesn't halt. It executes the next instruction, depending on how deep a instruction queue you can put in. Those are all choices you can make. And they don't have to depend on your instruction execution engine itself. That engine is one thing. These are all independent pieces. Of course, the pipeline depth you have to fix. In the design that we are going to do, I fixed the pipeline depth at 3 cycles. But you could put more. You could put 5 cycles and have a much deeper fetch engine. Getting back to the instruction set, we shared a summary sheet for the instruction just to get a sense of its orthogonality and so on, and also to get an idea of the number of instructions and the instruction types. But here is what you actually have to do. You have to make a detailed Excel where every instruction is a row and there's 1 column reserved for each bit. So this way you have all the instructions. I have shown this. This is a snapshot of the actual Excel. I couldn't open the Excel here for some reason, but this is the actual snapshot of the Excel. And I've not showed all the instructions, as many as I could reasonably capture. So I was talking about, if you remember, I was talking about the last 2 bits. If you can see the first 2 bits, the 0, 1, they are all ones in these instructions. And you would also notice that the first 6 bits, 0 to 5, are never all ones. When they become all ones, then depending on whether the 6th bit is a 0 or a 1, it's either a 48-bit or a 64-bit instruction word. Since these are all 32-bit instructions that we're talking about, those will not be all ones. So that's how the instruction fields are defined. And when these LSBs, the bit 0 and bit 1 are not all ones, it's a 16-bit instruction. So these are all the instructions shown here, and every field is shown. The advantage of doing this is you can do a very decent sanity check. You can compute based on each one of these bits. You can compute the actual opcode value and make sure that you do not have overlapping opcodes, which could happen if there were, for example, a typo in the original document or a typo while entering it here. You can do those things very easily using Excel. Then you can sort it out and figure out where the vacant opcodes are there, or if an opcode has been used twice. And you can go back and find out what caused it and fix it and so on. This is a very low cost and easy method of doing something that would later require very expensive cycles while verifying the detailed logic. Plus, there's also another advantage of using this Excel, is that the various bit patterns that you get out of here can be directly read out from a Python program, for example, that you could write, which we will talk about briefly, while you're generating control for your final data path. And those will pick directly from here. So you don't have to enter this data multiple places or multiple times. So this is the first and the first significant way from which you're translating the information in the ISA information in the document, which is a Word document or a PDF or whatever, into something that can be computed, which is an Excel. It's a painful work, but it has to be done. Fortunately, because it's RISC, you have to do that only for 48 or 50 or whatever instructions that are there in this particular case. If sometimes you wish to add a few instructions, you would add some rows here as well. For example, the one which is the fifth or sixth line, which says LFWS and LHWS, those two instructions are instructions that I added for some reason. Okay, we won't talk about that, but I added that. And similarly, there are, in that same background color, there are two more at the bottom, somewhere down the middle, which is SFWS and SHWS or something. So these are instructions that you could add. When you add those, you will have the corresponding opcode bits. And if you made a mistake and you used up opcodes which are already reserved for something else, you would find that purely at the Excel level. So this is something that is worth considering. At least it simplifies and eases your design verification phase after the logic design is done, and you're able to do it at this level. Having made the Excel, the next step is to make some design decisions. In order to write the flowcharts, you have to have some core logic that you would anchor your flowcharts around. So I call these the initial design decisions. And you have to recognize first that the underlying logic that will implement the ISA is not unique. That's very critical to understand. You can have different pieces of logic which will implement the same ISA. It's good in a way because it allows you to be innovative, and two microprocessors implementing the same ISA could have vastly different footprints depending on how cleverly you are able to do your design, and how well you're able to set up the underlying logic. The flowchart will help you to improve it, but your innovation plays a big role. As I had described earlier, we could assume that the register file is single, dual, or triple ported. You could even assume it is much more number of ports with the way you set it up. The first thing that one does while looking at the instruction word is that you would find that some data path elements are obvious. You would either design those data path elements or you assume they exist. I prefer that you design these elements. Or if you know they exist, then you incorporate that, identify that as the element. For example, you may already have previously designed an ALU, a 32-bit ALU. So what you would need for the flowchart, what you would need is all the control points for that ALU. So if the ALU has the data ports as well as the control points. If the ALU has two, the ALU will have two sources. It will have one output. And there'll be a whole bunch of control signals that will tell whether you're going to perform a logic operation, arithmetic operation, whether the arithmetic is 2's complement or integer or things like that. So you will need all those control signals. Those control signals are required to be at the time when you write the flowcharts. At a first level, you might avoid doing that, but as soon as your flowchart for any specific instruction reaches some degree of completeness, you would need to enter some entries. We will show that. Okay, and you'd also need a high-level view of the various delays and control points. So when you say that I'll build a 3-stage pipe, how much is the delay of one stage of the pipe? That you would have a data path in which you would say, okay, I think I'll put a single cycle multiplier, and the single cycle multiplier's delay is the maximum, is the critical path, and that will be one stage of my pipe. And therefore, all other stages I will cluster the logical operations, combinatorial delays of the logical operations, so that each one of the other stages occupy approximately the same delay as that of the multiplier, single cycle multiplier. Do you need to do the detailed timing logic design? No, probably not. But you need to have some sort of a sense, in the sense that when you look at a multiplier's critical path, you know exactly how many muxes and how many full adders are in that path. And accordingly, you obtain an estimate. And then you look at an ALU and you find out how much you get, and you find it turns out the ALU is maybe only 75% of the delay of a multiplier. So it means that you could add something more in the ALU's path. And guess what? You will need it, because when you're looking at branch or other instructions, there are these conditions that are being generated, and those conditions need some other pieces of logic that is best fitted inside the ALU. So do you know these things without doing much detailed design here? You know these things at this point of examination of the instruction word. So you create a data path with at this level. In addition to that, you also define some sort of a timing scheme that that you want in place. I'll show that data timing scheme, and recognize that as you go along the design cycle, you will change the timings. There's quite a possibility that you will change timing. Sometimes you might find something really critical, and then you say that, maybe I should go and do a very detailed design of this data path element and verify that the assumption I'm making in my flowchart is consistent with what I will get out of it. And if it turns out you won't, you'll have to readjust your data path, your pipeline stages. And so to generate the timing signals, again, to improve your design productivity, to generate the timing signals, you could use some kind of a generalized timing scheme to produce that. So this is the timing scheme we adapt for our design. This has a main clock, which we are calling the root clock, and the three stages of the pipe are partitioned into 4 phases of the root clock per pipeline stage. So the 3 cycles together amount to 12 quarters. And the way we operate the design, the design, there is something called a PC clock and something called a CISC clock. The PC clock is a divide by 2 of the root clock, divided by the negative edge of root clock, and CISC clock is a divide by 2 of the root clock, and this is on the positive edge. As you can see here, that each one of these clocks are you have resolution. You're using the PC and the CISC clock, but you have resolution of the original root clock. So the critical path is 2 cycles of the root clock, and you could potentially have a critical path, or your worst case path could be only 3 cycles of your, or 2.5 cycles of your root clock. And then what would happen is that the notion of pipeline might become invalid. You could have one instruction that runs for 3 quarters. There could be another instruction that runs for 4 quarters, and you could actually run your logic basis these durations in the pipe for each one of those instructions. So the notion of pipeline might, the pipeline being a 3-cycle, 3-stage pipeline with 12 clock quarters and so on, might become a superfluous definition. Not that we are going to use it here, but you could potentially do that. So that freedom is available to you, because it's naturally available to you. You can use it if you wish to. But this is how we set this up. So this is our initial data path. Basis this, you can form a data path. Now, I'm not going to show the entire design cycle, so I will skip some steps as we move along the design, but you get a sense of it. So let's see the next one. So this is, as you can see here, just so you know, that there were many versions of the data path, because every time you form a data path, write some stuff, you realize that there were some things you missed when you write your flowcharts. Then you go back and fix it, make another version of the data path and redo the flowcharts that you did before. We'll talk about those flowcharts and show some examples, and then come back and fix this and keep on moving. And this is an iterative process. And this data path, we drew this in using LibreOffice. You can do it on paper. You can do it, whatever you wish to on PowerPoint, and that's all there is to it. So now, as you can see here we have basically three parts in this data path. The extreme right part is what you would first form when you examine the instruction words. This is your the instructions directly imply this right part of the data path. As you can see here, there is, we define this as having three buses actually. One is the C bus, which is the destination bus. One is the A and the B bus, which are the two source operand buses. And you can see on the extreme right, there is one piece which has a plus written inside. That's the ALU, arithmetic logic unit. There is another, so there are two pieces which have the plus written on it. Look at the one which has which hits the C bus. That's the one I'm talking about. That is that's the ALU. Next to that is a cross. That's the multiplier. Then there is another piece of logic called the barrel shifter. And then there is the integer register file, which is the IRF. On the right side, there is a ALU. That ALU is intended for CSR instructions. There is some specific, if you examine the instructions, you'll realize that either you route it through the ALU in the integer ALU, or you have a separate bus for doing that. If you put it into the integer ALU, you lose a lot of cycles. Here you can save some cycles. So many iterations go on that. And then you have this CSR register file, which is shown next to it. And the CSR, again, similarly, has one input coming in from the B bus, and it writes out into something called the CSR bus. This integrates to when you try building a microcontroller based on your thing, based on the RISC-V, so these will integrate into some of the other elements in the microcontroller. So you have that. Then there is the central piece, which is an implicit piece, which again we have to infer when we write the flowcharts and so on, which is that as an instruction is fetched, you have to increment the address, you've got a PC increment, and when there is a jump, there's a different kind of thing that happens. If you get a 16-bit instruction, there's a different kind of increment that will have to be done, and so on. Or when you've got a memory, instruction memory is 64 wide, you have to do it slightly differently. So all those functions are inside another piece of logic. We can call it the PC incremental logic. That's the central piece, which is kind of highlighted in peach. Background is peach. And the extreme left is the memory interface. There's a DMEM, which is the data memory, and there's the PMEM, which is the program memory. Program memory is intended for your instruction fetches, which is the implicit loads, and the data memory is for data read and write. So can you write to program memory? Sure you can. So there has to be a path provided for it. So that some of those muxes and other things that you see there are intended for providing those paths. And again, this design was done a kind of a longish time ago. At that time, the relocatable code was defined to work under the base and bound scheme, which has since been changed into physical memory protection mechanism, which is now in place, where you could also do this base and bound as a specific implementation of the program memory, physical memory protection. But you can do that. There's a whole bunch of config registers under CSRs in the privilege mode, where you can set pretty much at very close resolution, I think 4 kilobyte resolution, you can set memories where each memory chunk of memory can be programmed to be readable, writable, read-write, or executable, and all kinds of combinations for each one of those. So if a particular program memory, particular zone in program memory is writable, you could actually write to that memory. And similarly, if it is readable, you could actually do a load store from that. So all that mechanism exists in RISC-V, and you'll have to define that in terms of the register transfers that you will support, and therefore the corresponding control elements. Each one of these elements that we have shown here in this data path I have not shown that here, but in your Excel, you will write out the control signals for each one of those. So every piece of logic here has a data port, some data coming in. If you look at the instruction for integer register file, I have not shown that here. There is an output. As you can see here, the IRF shows that its output can go to one of two buses. It can go either to the B bus or to the A bus. Does it mean there are two different ports? Can it happen simultaneously? You have to define that. In our case, we defined it not to be simultaneous. So it means that there is only one output that you can read. That you can read the. I'm sorry. We did it so that we have both outputs. The instruction register, integer register file can be read out simultaneously. Two different addresses, registers can be read out into the A and the B bus, so that that data can be propagated into the inputs of the ALU at the same time. Now, when you're writing into the register file, there, as you can see, there are two inputs that is shown, one from the C bus, one from the CSR bus. So can you write to two locations at the same time? No, you can't. But you can select one of those two sources. So the integer register file can take can write the output from the C bus, either the barrel shifter's output or the multiplier or the adder's output, and write it into the register file, or it could take the output from the CSR, but it won't be able to do both together at the same time. So this is not shown, this detail is not shown. Somewhere you would write it down, and when you're writing a register transfers, you'll remember. How much detail should you put in and how much detail should you abstract? Up to you, your convenience. For example, in this IRF, I have not shown a control signal, for any of these I have not shown the controls, but specifically for IRF, or for the, not for the IRF, for the barrel shifter, I have not shown the count input. So the count is coming into the barrel shifter, how much you're going to shift by. That is not shown. It's a control input, right? But it's not shown here. Okay. Again, in the barrel shifter, we are showing two inputs coming in from the B bus and the A bus. So there are two potential sources into the barrel shifter, but at any point, the control is not shown. So there are things you might find it necessary to show the control, or in some version of the data path you will show the control until you're done with the register transfers. Then abstract it out when you no longer need it. So you will have different versions of the data path as you move along. Okay, so this is how the flowchart looks like. I've shown this here for register transfers for ALU. In this, time progresses horizontally. So you can see Q1, Q2, Q3 right at the top. So this is horizontal movement. So three cycles of the clock will take you up to Q12. And spatial resource allocation and conflicts are viewed vertically. I have not shown that here fully. But what you see here is only for one register transfer, which is for ALU operation. And in order to find out whether there is, the way we have structured it, whether there is any resource conflict as an instruction moves through the pipe, you would put other instructions below this in this framework. This I have used Excel. You can use something. Actually, you can use some very nice software you can build. That would be very useful, but Excel is pretty good, pretty decent to use. So you could use and put below this instruction sequence from, for example, let's imagine that you have another register transfer, maybe for a jump. And after an ALU operation, you wanted to put a jump. What would happen is that jump instruction, instead of starting at Q1, you would put it starting at Q5 and put it below this. Then vertically, you can see, if you're using color code for resources, if you see the same color code between two different instructions in the same vertical space, you know that you've got it wrong. So you have to go back and fix either or both of the register transfers. But here I've shown after we do, so basically you will do a 3 by 3 matrix. If you're looking at a 3-stage pipe, you'll do a 3 by 3 matrix of all instruction combinations. And you can verify the conflicts right here at this level itself, and keep adjusting your register transfers so that there are no conflicts. And then for archiving purposes, each instruction is shown here. So let's work through this. How do we start? We assume that time begins, for any instruction, we will assume that time begins when an instruction fetch has happened and a new instruction is sitting at the instruction register. From that point, our time begins. And where does our time end? Our time ends when we have written a new address to the program memory address register, and instruction fetch has happened. And that should happen if you're assuming, which we are, that the instruction fetch takes as much or slightly less than what the multiplier takes. Multiplier takes, we are setting 4 quarters as 1 unit, but the instruction fetch could be 3 quarters for the fetch. So we are, as soon as the address is set, we say that, okay, this instructions flowchart is over. Now, what is here at the bottom, at the lower half? These are, you don't have to fill this, you don't have to populate this table until you have reached some degree of completion with reference to the register transfers across all the instructions. But you form this. So here again, as you can see, we have written it for clarity from quarter 1 all the way up to quarter 14. And the entries, the rows from this point on are the control signals. So here we have shown 7 control signals, but actually for the whole processor, it turns out that there's quite a bit more than that. In fact, in our case, we have 35 control signals. So we have 35 control signals. So the entire processor is basically driven by all these instructions. Basically will have to put together the controls signal values for each one of these 12 quarters, 14 quarters, as you can see here. We'll come to that later. 14 quarters and for 35 signals. So that table, this flowchart will help us populate that table. Once that table is populated, we are ready with to design the control. And this is a systematic way to get there. I have shown only for 5, and for data path elements that are not being used by this particular instruction, those entries will all be 0. In this case, we have assumed that all control signals are active high. You can change those rules. Whatever rules you set up for yourself to be consistent, you can change those rules. So in our case, we have set it up in such a way that all of these are active high signals. So if it's 0, it means it's not used. If it's 1, it means that it is active, and for the duration that it is 1 is also specified here, in the sense that there's some signal which is not named here, which goes high for 2 quarters, quarter 10 and quarter 11, and there's another signal which goes high for quarter 4 and quarter 5. Are these the only 2 signals for this instruction? No. There are 35, as I said. So these are only 7. Those are below. I had not shown that. Those details are not relevant to our discussion. So I have not shown those. Another thing to remember is that this instruction, what are we doing? In the first quarter, we have what I call the atomic recode or the decompression. The atomic instructions are basically instructions that decode, much like the compressed instructions. They decode into 3 or 4 instructions, regular instructions in the RISC-V ISA. So you can think of the atomic instructions as being similar to the compressed instructions. So combinatorially, you will convert each atomic instruction into a sequence of 3 instructions. That is done combinatorially. So that combinatorial recoding is what we do in Q1. And along with that, in parallel, we also do the decompression of 16-bit instructions. So if you've got a 32-bit instruction fetch, then you might choose to put 2 such 16-bit decompression engines, because both of them can do in parallel. And at the end of that first quarter, you will have, if it's an atomic instruction, you'll have 3 instructions sitting there. The bit codes of the 3 instruction, 32 into 3. Or if it's a decompression of a 16-bit, you'll have 64 instructions. So you will have 64 bits of 2 instructions. Then the Q2 is reserved for, it's actually not Q2. Because of the color system, it doesn't show up. Actually, you could imagine that both Q1 and Q2 is used for doing this function here. What is that function? It transfers from IR to IRF the addresses associated with RS1, RS2, and RD, which is source 1, source 2, and destination, which are direct fields in the opcode. And it also transfers to the ALU, which is the ALU's control signal, the FN3, the function 3, and the function 7. Those bits are transferred directly to the ALU. These are taken straight from the instruction. And in Q3 and Q4, what happens is the actual register transfer. Now you've set up the addresses. Now you transfer the source through the A bus into ALU input 1 and source 2 through the B bus into ALU input 2. And note also that then once this is done, ALU operation begins and you give it so much time, which is 4 quarters, to perform its operation. Now what you need to understand here is that at this level of abstraction, this ALU operation could be anything. It could be an add, signed or unsigned add or subtract. It could be an AND or any other logical operation. It could be a multiply, signed or unsigned. All of those at this level of abstraction is captured in the same flow diagram, in this same flow chart. What is not captured in this flow chart is if it were an add or a multiply or an operation with an immediate operand. That is not captured here. That should be a separate register transfer. I have not shown that, but I'm just explaining that. In the next few slides, I will show a few other instructions. After this ALU operation is done, you transfer the ALU output into the through the C bus into the destination register, which is in the IRF, which address has already been set up in Q2. And so between Q2 and now, that destination address cannot be changed. So if some other instruction is attempting to use that here, that instruction will find a resource conflict, or should find. You will find the resource conflict and readjust that the variations. Then comes the Then if you see here in the last 3 rows, we have some operations which are shown, which are these housekeeping operations. So you will do a reg PC will be incremented by 4. So it points to the next 32-bit address. And it writes that incremented by 4 is written to the memory address register so that the memory instruction fetch can begin. At the same time, the PC is incremented and stored in reg PC. Okay, so we have 2 different terms. There is a reg PC plus and a reg PC. So those are all details. When you start writing the register transfers, you will realize that some places you have to keep duplicate registers. In some places you have to do a provisional increment so that that information can be transferred at the right time or discarded. So there are those kinds of functions here which we've not written, but when you start writing which we have not described, but when you start writing the register transfers and keep the data path by your side, data path drawing, which I showed you, when you keep it by the side and start writing, you realize that there is some hardware resource has to be put into your data path. Otherwise, this function cannot be done. Or the expectation that you have of that function will not execute. You will need more cycles to do an instruction, for example. Here what our target has been that as many instructions as we can, ideally all of them, should execute should have a throughput of 1 cycle. Meaning that if I put ALU ops back to back in the 3x3 matrix, if all are ALU ops, they should all function without any conflict, such that after an initial latency of 3 cycles, I should be able to get 1 instruction out at a time per cycle. So if you want to do that, then there are certain things that will have to happen on the housekeeping tasks. And that certain thing is what shows up in this PC plus PC. It's there in the data path though. If you look at the data path a little carefully, you will find those things there. Okay. Now, if you see that this, the memory address register, we stretch that into the 13th quarter here. Is that realistically possible to be done? Because the 13th quarter really is the Q1 of another set of 12 cycles. So this is the beginning cycle. You've stolen that cycle from somewhere, from somebody else's instruction. But not just that. If you had these ALU instructions back to back, this one would be on the 13th cycle, it would also be on the 5th cycle, it will also be on the 9th cycle, because the previous and the previous instructions would have this operation filling up there. So during those phases, if the data path has no conflict with that particular resource, this resource does not have a conflict, you can potentially do that. So we have done that. So although it's taken one extra quarter somewhere, because we found out, because of the critical paths and all that, we found out we needed a little bit more, but we can pull this off. So this is done. Now this one is for the ALU instructions. I'll show a few more after this. Let's see the next one. So now let's look at another instruction. This is a jump instruction. Jump with the current PC or the next PC stored in a specific register, in the destination register. So this is the kind of instruction you would use to represent a subroutine call. Now the initial portion stays the same, excepting that this register has an immediate offset, which offset needs to be added to the source register, which is there in RS1, and that becomes the new PC. And the current PC, whatever the next instruction that the PC would have fetched, should be stored in the destination register. Now understand that this is a pipeline, and therefore the PC is currently far ahead. It's pointing to the third instruction ahead in the queue. But when the jump happens, the next two instructions are not going to get executed. So the PC has to be set up so that it points to the instruction which would have been, which is immediately after the jump instruction. So all that manipulation has to be done inside the in the PC increment section. And the immediate so as you can see here, we've shown something that RS1 through the A bus goes to a register called JRS1, which is there in the data path. And IMDAL is immediate data alignment logic. So from the this is happening in Q3, Q4. So from the instruction register, you have the immediate data alignment logic, which is a piece of combinational logic. As you can see in the instruction for the immediate data, they are all misaligned, scattered all over the place. And you have to align those, and it's very simple logic. Basically a bunch of muxes that will enable that and put it into the right location in the corresponding bus. So that immediate data alignment logic use that data alignment logic to write directly into another register known as the base offset register. So that offset is added to the GRS1, and that becomes the new PC. And the corresponding PC, we have stored it somewhere, the corresponding PC, which relates to the PC that would have been fetched, the instruction that would have been fetched in Q5. That PC is stored in the destination register. And in Q5, what we do, Q5 and Q9, what we do is we disable the PMBR and force, PMBR is the program memory buffer register. We disable that and force NOP into the instruction register. So the next two instructions which could not be fetched, or the instructions that were fetched and could not be used, those instructions are forced to be no-ops, and then the current instruction executes just like as the other cases. The current instruction executes and sets up the pipe. So after these two instructions are done, the next instruction will end up being the destination register on the jump. And the return is also a similar kind of a jump instruction, where the register becomes, the RS1 becomes what was the destination in this case. And one could potentially put an offset of 0 or put a negative offset and go back to that particular instruction that was not executed in Q5 here. So depending on how you do it, you can set up the program appropriately, how you set up the hardware. And as you can see here, again, the control signals, there are some of these control signals that are active, and you can see here, there's one control signal that actually crosses a cycle boundary, not just a quarter boundary, but also a cycle boundary. These things can lead to glitches if not implemented properly in control, but there are very simple ways to sort that out so that there are no glitches. And okay, So now let's see. Let's look at the next instruction. This is the load instruction. Again, here in this case, I've shown some of these control signals, those first 4 or 5 control signals. These are the names here. And again, this does the same kind of function as with the other registers, excepting that in the case of a load, there is a data memory read in between, and that data memory read is stored appropriately. And there is something here called the LDAL. This is the load memory alignment, load alignment logic. So when you're loading something, you could load a half word, you could load a full word, and in some cases the half word may need to be realigned to the lower 16-bit before writing into the ALU. And this is again very simple combinational logic, and one puts that into the bus itself. Let me see. This portion that you have here, I forgot to mention that earlier. This portion that you have here between Q10 and Q12, which is the housekeeping task, reg PC and all that. Remember that whatever we've got between Q10 and Q13, if you stack these instructions in the pipe, this is going to be repeated. This is basically 4 quarters, basically 1 cycle. And if you repeat this, this will be there for instructions previous in the queue and the one previous to that in the queue. This portion will be completely filled up. So it's not as if this piece of logic is being used once every 14 cycles. In a pipelined engine, this is being used continuously. So also true with each one of these other pieces of logic that we've written, excepting for a data memory read, which may not happen every cycle, unless there is a requirement through a load or a store, or an ALU operation, which would probably happen every cycle so long as you're doing computation. But when you're doing a load, at that time, the ALU might not be used for one particular bubble of a 4-cycle window somewhere. And now let's see the next one. This is a store, more of the same, and similar kind of a description as you can see here. This is a branch, again, a little more complicated, because in this particular case, you actually end up, if a branch is not taken, it becomes much straightforward. And if the branch is taken, so what we do is we compute in this particular scheme, we show that the branch, we compute obtain the branch destination, assuming that the branch will be taken, so that the final decision is simply a mux. That way we save a little bit of time in terms of the whole operation. There are other clever things that could happen, both in the case of branch as well as in the case of a jump, that the offset is 4 kilowords. So imagine that you had a cache on chip, and RISC-V ISA tells you that it is expected that R1 or R5 will be used for these kind of, for the link register in case of subroutine calls. If you assume that it is being used and somebody has written a program that kind of complies with this, then what you could potentially do, and they have said that you can, they recommend that you can do it if you want to put in the hardware resources. What you can do is you find out what your RS1 is, and in parallel, whenever the memory is kind of not being used because you filled up the queue and instruction execution is moving smoothly, you could actually load 4 kilowords from memory into an instruction cache. Now, when there is a branch or a jump, and it turns out that the RS1 is the R1, then you have all that information sitting on your chip, and you could get hold of it at much lower cost than and therefore time than doing a full-fledged memory fetch. And if you didn't have it, somebody is using another register and you didn't collect that, then you go through the whole cycle. Or you're building a really, really low-end machine and you don't want to do all this caching, then also you go for the full cycle whenever there is a jump or a branch. So now let's see what's... Okay, so this is version 20 of the data path. It captures all the register transfers we've shown till now. It's not the final version, but close enough to the final. And all the stuff that we spoke about in the last several slides are captured in this version. As you can see here, there are several things. First of all, let me see, can I get a pointer here? Yeah. As you can see here, we have now expanded on this portion. We are now showing the 3 pipeline stages for the instruction register. So all these instructions are captured in, because different bits of the instruction register are going to be used in different cycles. So the control engine will need not the different bits that are needed in the appropriate instruction word, which could be in the current cycle or the previous and so on. As you can also see here, there are some other elements that have been added in here. For example, the divider, which wasn't there before, is now shown up here. Let me see now. We spoke about the immediate data alignment logic, that is this piece here. We also spoke about the load data alignment logic, that is here. Then we have the store data alignment logic, that is here. And as you can see here, the different elements here have different colors, and these colors, there are 4 of them, these represent the different phases of the clock. So which phase of which clock is being used to latch the information is captured in the color of the register. As you can see here, the positive edge of PC clock is the dark green, the negative edge is the light green, and similarly for orange and the peach. So we spoke about the jump instruction. As you can see here, this is the JSR. This is the JSR, and this is the base offset register, which is written in directly from the no, sorry, that's the PC. Where is the base? Here is the base offset register. This is the base offset register, which is written directly from here. As you can see on this red line, this comes from the load data, immediate data alignment logic. So this comes from here, it writes into the base offset, and depending on what the instruction is, if it's a jump instruction, it picks this, otherwise it picks the PC, and then one of those gets multiplexed, and this gets added and produces the virtual memory address for the next instruction, and this one gets added to the base and then compared against the bound and so on, and goes into the becomes the program memory address register. The same value also goes round in this cycle, whether it's a 16-bit instruction or a 32-bit instruction, suitable increments and all that, and they are kept in here. Various other versions of this are kept here, so they can be used for into the ALU and so on. The registers that we spoke about, all these register transfers. And let me see now. Yep. And so you can see here that there is these special paths, these ones that are shown in red, are special paths that were created between version 16 and version 20 to speed up certain operations. If these were not there, a set of register transfers could still be written, but would, for some critical instructions, would still end up taking a few more cycles than it currently takes. As you can see here, this is the decompression logic that is shown here, and into the decompression logic you can see are 2 inputs coming in. These are each 16-bit inputs, which come in from the instruction fetch bus from the PMBR. So these are sequenced suitably into the decompression and appropriately pushed into the IR. And the atomic decode we had described separately. I have not shown this here because this piece of logic is implemented, but we have not integrated that into this system, because that piece of logic, for the version that I designed this for, we didn't need. At this point, what have we achieved? We have completed the flowcharts of all the instructions, and along with that we have obtained in every flowchart all the control points, the 14 quarters of values for every single control point. associated with a control point in the data path, and we've done that for each one of the instructions. So at this point, the control is unambiguously defined. Now, how do we design the control from here? We can design it in a number of ways. I will show one method, I think, which is a very simple, straightforward, easy to visualize at this point. So what we have is, imagine that at this point, in each instruction, we showed 14 quarters and we showed all the control signals. Actually, what we have to do is we have to create a control matrix in which each row is an instruction, and we have 14 quarters times the number of control points. So we got 35 control points into 14. We have that many columns for in our table. So we transpose the entries from each one of these instructions into this particular table. So for every instruction, we have 14 into 35 columns, and we enter those ones which we obtain from each one of these flowcharts. Which is manual work, unfortunately, but after this table is done, this table can be read up to create our control. Let's see how. We do it in two more steps. So the first thing we do is we create something which we call the instruction signal. The instruction signal is the output of an AND gate, and there'll be as many AND gates of 5 or 7 bits, depending on how you structure it. 7 bits, let's say. There'll be as many AND gates of 7 inputs as there are unique instructions in the to be implemented. So at the output we have as many signals as there are instructions, and each of these signals will be a high when that particular instruction is true and will be a 0 otherwise. These instruction inputs will be we will construct the control logic by ORing the instruction opcodes of all the instructions for which the corresponding column entry is 1. So we will do this for Q1, for Q2, for Q3, and so on, for all the instructions for which the corresponding column entry is 1. We do not mix up the columns right now. That is, we will finally get n signals for each control point, where n is the number of quarters that we are addressing. For in our case, there will be 14 signals for each control point at this time. Now, these we will AND for all the non-zero entries. And once we AND these non-zero entries, this will become a the signal for a single control point. And that will feed the control point. Now, how do we achieve this? We can do that by by writing a Python code. That's what we did. We wrote a Python code for this, which directly reads the Excel and generates all these signals, which will generate the Verilog for each one of these gates and outputs a bunch of logic which relates to the control output. And that is copied and pasted into the Verilog code for where up till now, where we put in all the data path elements. We will put that in, and our data path and timing, we put this in, and our logic is ready to operate. We can then start, we have done that. You can put that and start executing programs. You can start, now the processor is ready. You can write a program and bring up the Verilog and execute it, and the Verilog will execute that program. And you can write any set of programs. You can link it to the output of the compiler, of the C compiler, write a program in C and download this. There's a little bit of adjustments you have to do to relocate the code precisely inside the memory map. But other than that, you can start executing code from here. We have, when there are multi-quarter control signals, we can, there could be glitches that could happen at the transition of these quarter signals, but these can be eliminated. These glitches can be eliminated in a systematic way, and that systematic method can also be fully automated into the Python code. We have done that. Visualize that when people talk of a microprocessor design, there is this control. In the classical terminology, there's the control PLA, and what we have just implemented. Excuse me. What we have just implemented is basically an and or and plane, and the flowcharts have simply enabled us to systematically arrive at it. And interestingly, as I had mentioned earlier, since all these instructions are defined in rows, let's imagine you define a piece of code and you find out that there are a bunch of instructions you're not going to use, you just delete those rows. That's it. And while you're deleting those rows, you will also find out that when you look at the columns, if there are some columns where the control signals, 14, each control signal comprises 14 columns. So if some bunch of control columns happen to be zeros all the way through, it means that the corresponding data path element has not been used at all in that block. So you can get rid of those control signals and get rid of the data path element from your data path. Now you've got a piece of logic that is optimized for the function that you created, that you were trying to build. And this function is a proper subset of the RISC-V and can actually be incorporated into the RISC-V's toolchain. Of course, if you did such a thing, you'd have to go through the entire timing design and so on and so forth to customize this piece of logic. So the first thing which I said, that you only write code and so on, that piece may not work, but you have optimized this. You have a fairly highly optimized piece of hardware which properly fits into a RISC-V toolchain, and therefore is software compatible with the RISC-V toolchain, and its upgrades are automatic as the toolchain upgrades through multiple versions of the RISC-V, different process nodes, different technologies, and so on and so forth. So finally, what we have done is we have shown a method by which, a flowchart method, by which one can build a microprocessor from scratch. And we've shown this for a RISC-V, but it applies to any other processor. You could use it for a RISC engine. You could use it to build CISC engine. You could use it to build something else, for example, an ARM or a MIPS or something. And you can then customize it for different applications. You could potentially make array 2 of these cores and have a suitable modification to your instruction fetch to create a superscalar architecture. You could increase the number of pipelines, which would be a separate design. You could increase the number of pipeline depth and obtain a different processor. You could put an array of these processors and build, with a complex arrangement for your memory access. You can build a supercomputer if you wish to. Of course, each one of those will have significant overheads in terms of the prototyping costs and so on. But you have a building block, the Swiss knife, to put together and carve for yourself whatever piece of logic you need to build using this scheme. And this one, as I described, you could satisfy multiple objectives with it. A professor in an institute can use this to let designs migrate from one bunch of students to the next bunch of students and create an entire IP library in the open domain. On the other hand, commercial organization can do it internally and make incompatible pieces of IP compatible with be supported on a common toolchain framework. So it helps for design archiving, it helps for design reuse, and helps for improving the productivity of your design team. And while you do this, it's much fun to do this. Of course, as I described, the minimum tool that you need for doing this is a Verilog simulator. In my case, I used from Mentor, now Siemens, and Excel and some tool to draw the data path. If you had access, there are tools that are there. You could use those. And for example, very expensive, from Synopsys, there is this tool called the ASIP Designer. You could use that. which uses slightly different terminology than our flowcharts, but it should be fairly straightforward. I haven't done it myself, but I looked at it. It should be fairly simple to migrate it to the flowcharts, migrate the flowcharts into their scheme. But the payback is enormous because the toolchain automatically, toolchain, debug, single stepping, all those kinds of things that design for test, they get spit out by the software that sits behind the ASIC designer. So if you take the effort to do that and you have the resource to obtain such a tool, you could use that. There's also another one which I haven't looked at that carefully either, which also does a similar kind of thing from I think a European company called Codasip. They also have a similar kind of tool chain, but it is dedicated for RISC-V. So you can build a whole bunch of RISC-V stuff without having to worry about the tool chain that will be required as you build your own custom processors. So there is a framework for doing all of this. You can use this to develop logic of your own. You can use this to improve the productivity of your team, and that's it. And it's fairly simple to do, as I explained in today's call. Thank you, everybody.